Welcome back to the next Unit 2 video. As you can see, today we're going to look at some of the various transmission mediums. So a quick overview, we're going to look at twisted pair, coaxial, fibre optic. Those three are going to be wired. Right, then we'll look at Wi-Fi and satellites. Okay, those two are going to be wireless. Alright, so as mentioned, we're going to look at, I guess, the advantages and disadvantages of both wired and wireless, right, when we would use each. Right, then we're also going to look at, which transmission medium can be used for local communication, right, whereas, which is more suited for global communication. And right, we're also going to look at some key terms. So, for example, attenuation, bandwidth, repeaters, guided and unguided, also shielding, channels, and interference. And that's probably non-exhaustive, right? There's probably more than that as well. Alright, so as stated, then there's going to be two methods in which data can be transmitted between devices. Right, that's going to be wired, so twisted pair, coaxial, fibre optic, and I think we did briefly mention those in the last video. Although I think I made that nearly a week ago now, so I can't really remember too well. Alright then, wireless, so we're going to look at Wi-Fi, satellites, and also Bluetooth. I mean, Bluetooth is not really mentioned, I think, in the book that much. Although I guess you could list it as a wireless, sort of transmission medium too. Right, so some of the key terms, one is going to be bandwidth. This is a measure of the amount of data that can be transmitted per second, and this, the units is usually 1 megabits per second or gigabits per second. Now, I guess, people are, of course, familiar with, let's say if you have your internet speed, right, if you buy, sort of internet package, right, monthly internet package, they might say, well, we're going to give you a bandwidth of, let's say 100 megabits per second. So that's going to be sort of the maximum, incoming speed into your house. So hopefully that makes sense, right? It's just, if you think about physics, it's basically equivalent to flow, kind of how much liquid or how much gas is flowing through a pipe. Basically, it's the same with bandwidth. How much data is flowing through the system. Right, then there's going to be attenuation. So this is the rate at which the strength or intensity of the signal decreases. And I think right, if we just go back to this bandwidth, probably this will explain on the next page. But if we look here at the attenuation diagram, hopefully, this kind of makes sense what it's showing, right? So of course, as the distance increases, as the signal is traveling a longer distance, then of course the strength of the signal is going to decrease, the intensity of the signal is going to decrease. Alright, so let's try to think then, what factors do you think are going to affect bandwidth? And probably here, you can think of one, right? If we look at this, sort of example 1, right, versus example 2 here. Right, so let's try to think of the sort of cars on the road analogy, right, that we see in the picture. So, so I guess, one is going to be the physical speed of the, data transmission, or of course, right, if we're talking about cars, that's, the speed of each car. Because, let's say if we do a side-on view of the road. So let's say this is our road, and this is car 1, right, this is car 2. Now, of course, right, so let's say each car is going at 100 kilometers per hour, and let's say here this is our sort of detector. Then of course, right, each second we're going to detect lots of cars going past, right? If in contrast, the car's only going 1 kilometer per hour, then of course, we're not going to be kind of detecting as many cars. And obviously we say, the cars, right, that's going to be analogous to the packets, right, the actual data being transferred. Right, then there's going to be the frequency of the transmission, and you can think of that as kind of the distance of one car to the next. So if we have a road where, let's say the cars are really close together, then of course more cars are going past. Right, if we have let's say this example where of course right, where of course the cars are far apart, then of course not as many cars are going to go past per unit time. Right, you can also think, the number of active channels, and if you're thinking the car analogy, that's just the number of lanes. Of course, if we see in this example, we've got 1 lane. I guess if we see here, we've got 4 lanes. Right, therefore, if they're going at the same speed, right, if the frequency is the same, of course, right, that's going to that's going to be sending 4 times as much data. Right, and I guess, so in most cases, points 2 and 3 are the deciding factors, since both electrical and electromagnetic waves are, they're both going to propagate extremely fast. Now, I think we'll see in a minute, right, the actual difference between them. Alright, so if we think about attenuation, so what's going to make the actual strength of the signal decrease? So one is going to be the substance the data is transmitted through, so copper, air, right, buildings or walls, things like rain, right, vacuum. So if, for example, we think of vacuum, in this case, this will be good, right? Okay, right. Yeah, so if it's going through a vacuum, well, we can say the attenuation will be low, right? Yeah, maybe this sort of curve. Yeah, this sort of, linear. Yeah, I guess, linear gradient. Whereas instead, okay, if it's a wall, well, I mean, I guess, as it's going through the air, it's probably going to be okay. But of course, when it hits the wall, well, yeah, then we're just going to get a sharp drop. Yeah, I mean, likewise for rain, going through clouds. Right, that's why, yeah, I guess on a cloudy day, maybe you're going to get worse signal, yeah, from the satellites. Right then, frequency, well, so low frequency waves, right, e.g. radio, right, they're going to attenuate less than high frequency waves, right, e.g. gamma. And I think from physics, people probably know this. Yeah, just thinking that, well, yeah, those waves, I mean, they're going to get blocked more easily. Whereas, yeah, I guess low frequency, right, they can sort of travel longer distances. Yeah, they can travel through, sort of substances more easily, I guess. Alright, so if we look at the first specific example, well, one is going to be twisted pair. And effectively, I mean, this is also what some people call, Ethernet cables. Although, yeah, in the exam, okay, make sure to call them twisted pair, right? Don't call them Ethernet cables. Since technically, well, Ethernet is the actual protocol, right? Whereas, yeah, twisted pair is the actual, physical cables. Right, so twisted pair, well, they're going to have insulation and shielding. Right, that's going to, okay, so that's used to block electromagnetic interference from both the outside and also between the pairs. So I think what outside interference, I mean, hopefully that's kind of obvious what that's saying. That's of course just saying, well, obviously, yeah, sort of, signals coming in from outside, right? Yeah, electromagnetic signals coming in from outside. Right, of course, well, when it says between the pairs, well, that's saying, okay, right, here's the pen. Like, okay, so for example, right, this pair here, well, this is of course going to be sending a signal. Now, this signal could leak out, and, okay, this signal could then, leak out into these, sort of green pair, for example. Yeah, that's what we see, what they're covered in this kind of plastic, yeah, rubbery kind of shielding. And then I suppose this one, okay, here. So right, okay, so if we look at this one, well, this is going to be called unshielded, since yeah, we don't have like this additional metal shielding. Whereas, okay, if we look at this second example, well, this second example is going to have this additional metal shielding, or yeah, this additional, I guess, what aluminium foil shield. And that's just going to make it even more, I guess, kind of resistant, yeah, to the sort of, well, I guess, yeah, kind of external, right, electromagnetic interference. However, of course, well, this one is going to be more expensive, right, if we're also using this additional, yeah, aluminium foil. Right, okay, and we can also say, well, the twists are also used to reduce the electromagnetic interference. Then just for some more information, now actually this information is not required for A-level, but yeah, I think some people, they actually like to know the kind of underlying physics, right, the underlying, I guess, yeah, technique of how it's actually working. So here then we say, well, different cables are going to be twisted a different amount. And this is to keep wires out of phase to reduce, well, I guess, yeah, reduce crosstalk, right, reduce interference. And I suppose, like, specifically when it's saying crosstalk, well, that's talking about, interference, right, between the actual wires. Yeah, or well, I guess, yeah, kind of between the pairs. And I guess, like, if we actually look at this, I mean, I think if we see here, for example, okay, this blue one is twisted the most, or there's, yeah, I guess, well, sort of the distance between the twists is, the shortest. Whereas, for example, if we look at this brown one, well, I think this is twisted the least, or yeah, kind of, well, I guess, yeah, the lowest amount. And I suppose that, well, the reason for that is that, like, I guess, right, okay, if we're sending, let's say, at the same frequency, or yeah, I don't know, maybe a similar frequency, well, if this is twisted more, yeah, I guess, yeah, I don't know, we can say the, yeah, I guess the wave is going to be something like this. Whereas, probably this one, right, probably it's going to be a longer wavelength. And because they're sort of going to be going at different frequencies, yeah, well, then, of course, right, they're going to have less crosstalk. Yeah, I mean, probably a terrible explanation. I mean, if you want to find out more detail about that, of course, yeah, watch videos. I definitely don't have a PhD in physics or anything like that. Right, so, okay, all right, here it is. Yeah, so then we can also say, well, more twist is going to equal less interference, and, well, that's going to mean there's a higher frequency, right, and also less bandwidth. Yeah, because, well, I think, right, the higher frequency, well, this is like what we said with the cars, that, of course, well, if, I mean, okay, so if the cars are closer together, well, then, of course, it means, well, more data is going to be sent per second, right, there's, yeah, sort of a, I guess, yeah, a closer, right, okay, I guess, there's a smaller distance, right, between each of the peaks and troughs. Right, however, a disadvantage, well, more twist is going to mean more attenuation. And one of it was, right, actually higher capacitance. Yeah, and also, right, the greater length of the wire. Because if you think about it, well, of course, if you have a wire in a straight line, okay, so let's say we have a 1 meter wire in a straight line. Well, obviously, that can travel 1 meter. Now, if we have, if we have a 1 meter wire, but it's sort of, twisting up and down, well, then, the actual physical distance it's going to travel, I guess kind of the linear distance, right, the horizontal distance, is of course only going to be, well, say 0.9, right, so it's not going to be 1 meter, yeah, since it's also, moving up and down. Yeah, I mean, I think, well, hopefully that makes sense. And then I suppose, like, if you just want to see what it looks like, well, it's going to look like this. I mean, I think most people are familiar with these. Of course, used to, well, connect devices, right, to the switch, or I suppose, well, people call it router probably, but yeah, I guess technically, right, you would probably want to call it a switch, since usually you're using this to connect devices within a LAN, right? Whereas in contrast, well, a router, that's going to be used to send packets from, I mean, okay, right, I guess you can say, well, a router is used to send packets from one device to the next. Now that could be from, a device in the network. Obviously to, well, I guess, the ISP's router, right, then, another router, right, another router, just, sort of, well, each hop by hop, right, until it gets to the final destination. Right, so again, right, of course, this is not required for the exam, but basically, if we think, okay, well, so why are there two wires, right, why is it a pair, right, why is it not just a single wire? So what they do is, well, on one of the wires, okay, they're going to send, I guess we can kind of say like the positive signal, right, just the, I guess the sort of standard signal, right, then on the other wire, okay, well, then they're just going to send the inverted signal, right, the opposite. So whereas, I don't know, this is, say, 0.5 at this point, of course, well, this point is going to be, right, minus 0.5, so yeah, it's just inverted. So what we say then, well, the signal, okay, right, so a signal sent on the red wire, right, an inverted signal sent on the blue wire. Right, then it's the difference between them that's actually the final signal. So in this case, I guess, here we are. So, right, okay, so at this point, well, it's going to be 0, because, I mean, well, so this is 0, this is 0. But then at this point here, well, basically our signal is going to be 1, right, because, well, if this is, positive 0.5, right, this is negative 0.5, well, then, of course, the total distance between them, right, is going to be 1. Right, so if they were not twisted, then, well, outside electromagnetic interference, or signals, would hit the wires, hence they would induce current at different times. So we would have something like this, where I guess if you see here, right, okay, this is our sort of curved, right, this is our curved electromagnetic wave. Now, since, of course, A is actually closer to this wave, right, therefore, of course, right, this, outside interference is going to hit this wire first, right, and that's why we get the little spike here before. And well, then of course, it's going to travel down to B, right, and of course, I mean, that's going to, sort of, I guess it's going to induce the current after, since, sort of different physical distance. Right, in contrast, like if we twist them, probably it says, okay, so if we twist them, well, this will ensure interference occurs at, I guess, kind of roughly the same time, right, hence the difference stays the same, because if we see here, and I guess, I mean, it's not exact, right, because obviously, well, here, this is, well, it's going to hit this right before it hits this one. But if you kind of average it out over all of the twists, because, well, obviously, okay, so obviously, right, here it's going to hit the red one first. But then, obviously, when it gets here, well, then it's going to hit the blue one first. So I guess if you kind of average it out, you can sort of do some processing based on this, to work out what's interference and, what's the actual original signal. And like what we're saying is because, well, basically here, right, if we both have the same interference, then if we actually think about that, well, the difference between the wires has actually not changed, because, all right, okay, so, all right, so let's say this is our two signal, and okay, let's say the distance between them is just 1. Now, if we then have a spike here, and we also have the same spike here, well, if you actually look at this, okay, well, the distance is still 1, right, since both of them have been affected by the same amount. That's going to be why they're twisted, right? Although, of course, again, right, this information is, right, not needed for the exam, right? I mean, this one is, although to be honest, they would rarely ask this, to be honest. Right, so, well, shielded twisted pair. This also contains, well, metal insulation, right, I think, as we've seen, right, just to, I guess, further prevent interference. Of course, well, I mean, here, right, this is the metal insulation, and I suppose, right, also, metal insulation, right, between the individual pairs as well, just to prevent crosstalk. So right, okay, so if we say the metal insulation, right, sort of, I guess, around each pair, well, mostly that's going to be to reduce crosstalk between the wires. Whereas, of course, if we look at this kind of outer one, well, of course, I mean, this is about what external interference, right? Reducing the external interference. Right, however, the disadvantage, well, it's going to be more expensive. It's also usually not necessary, because I guess, most environments actually don't have that much electromagnetic interference. However, where it can be used, well, it can be used in data centers, because if you've got, sort of thousands of servers, well, I guess, yeah, obviously there's just going to be so much, electrical signals or electromagnetic noise, then in that case, yeah, you probably would want, this shielding. Right, also places with high frequency wires, right, or yeah, places like factories, right, environments with, I guess, well, lots of powerful electronic or yeah, magnetic machinery. I think they also said that hospitals. So a lot of hospitals, what they're, well, I guess, yeah, maybe they got some, X-ray scanner, right? Of course, that's, electromagnetic waves. They've got things like what the EMI, is it the, yeah, electromagnetic something? So yeah, I guess kind of like the brain scans or, whatever they're doing. So places like that, right, they would also probably want shielded, yeah, just to, reduce that outside, yeah, interference. Right, so twisted pair, right, there's, well, I guess, yeah, various different categories. Category 3 is going to be the slowest, right, category 7 is the fastest. And actually what we see then, well, the difference between them is going to be, well, it's going to be the maximum speed they can handle. Or I suppose, well, when we say speed, right, I mean, well, bandwidth, right, bandwidth is probably a better word for that. Right, without having any crosstalk or interference. And the numbers represent the tightness of the twists, right, that are applied to the wires. So of course, well, here we're saying, what, more twists. And I think, yeah, more twists is going to be, I guess, faster. Right, so I guess, well, category 3, right, is, well, the slowest, right, category 7. And what's that? That's going to be, yeah, right, okay, so what that, that's going to be 1,000 times faster. So yeah, we're going from, 10 megabits per second, right, to, 10 gigabits per second. Well, yeah, of course, this one, well, this gigabits is 1,000 times faster, right, than the megabits. Right, okay, and then, well, I guess we've also got category 8, right, that's even faster. Right, I mean, so that, well, okay, yeah, that only has a short distance. And if we think, well, the reason why this is good, or yeah, the reason why it's, well, the ultimate copper cable, as they say here, well, one, that's because it's shielded, and I guess, well, obviously, what the twists are going to be, quite close together, and yeah, I guess we see, right, the speed is, well, fast, or yeah, the bandwidth is high. Then let's just look at some of the advantages and disadvantages. So the advantage, well, is it's going to be cheap. And I think most people probably know this, of course. Well, when you get like a, yeah, probably, I don't know, when you get a PlayStation, I think a lot of them previously would have come with, a twisted pair cable like thrown in. Well, yeah, maybe you just get it, added on for like an extra, sort of low price. Right, however, the disadvantages, so, I mean, really the advantage, right, well, it's cheap, that's basically it. Right, disadvantage, well, low, I mean, well, okay, let's say, yeah, low bandwidth, right, lower bandwidth. Although this I'll put in orange because, well, this is kind of relative. Now, if we go back here, what we saw, the category 8 can support 40 gigabits per second. Now, if you're talking about, just a sort of home setting, right, yeah, I guess, well, in your house, right, I mean, maybe even in your classroom, right, some, yeah, small setting, then, I mean, honestly, like 40 gigabits per second, I mean, well, that's going to be more than enough, right, I mean, that's overkill. So, in those kind of simple environments, it's fine. Now, if you're talking for, like, I don't know, yeah, I mean, let's say, like, an office with, 1,000 people, well, then, right, maybe that's not going to be fast enough. Likewise, of course, if you're talking about, transferring data between, different countries, for example, via the undersea cables, well, yeah, again, right, 40 gigabits per second is not going to be enough, since, this is probably going to be shared between, like, millions of people, yeah, if it's, for the undersea cables. Right, and I guess, well, okay, so, yeah, kind of more obvious, right, disadvantage. Well, right, high attenuation, so, yeah, this is definitely true. Right, we can also say we're strongly affected by interference. So yeah, even the shielded version, right, is still not going to be completely unaffected. Right, it's also going to require many repeaters. Now I think repeaters we haven't actually mentioned, but if we just think so, right, yeah, let's try and draw this graph again. Okay, so well, this was distance, and then I suppose what on the left, what on the y-axis. Let's just call it the intensity, right? So the intensity of the signal, and I think right in the chart they kind of drew it stepped like this. So of course, I mean, what right? Okay, so I guess as we're saying then, the over distance, well, of course, yeah, the intensity is just going to decrease. And remember, I mean, well, okay, right, that's just what attenuation means, right? Yeah, the signal strength is decreasing at over distance. So what we're going to need, well, we're going to need a repeater because, well, of course, otherwise it's just going to go down to 0. So you'd probably have a repeater, I don't know, like maybe this position here, and yeah, let's use a different color. So what's going to happen is, okay, so all right, so when we measure this signal, basically, well, this is then just going to get boosted back up, to the original value again. Right, yeah, okay, hang on, right, just, yeah, ignore this one. All right, and then, okay, so, yeah, okay, all right, so let's say here, well, here then we're probably going to need another repeater. So, of course, yeah, that, again, it's just going to get boosted up. Yeah, all right, yeah, not like that. So hopefully that makes sense that basically what you're going to have is, I don't know, maybe every sort of, well, certain distance, right, you're just going to need a repeater. Now, I think for twisted pair, you probably wouldn't use this because you often don't have situations where you're using twisted pair for like, you know, some huge distance. Um, I think something like fiber optic, right? Fiber optic, I think they say every 100 kilometers you would need a repeater. Yeah, twisted pair, you know, I don't know, maybe every 50 meters, right? Maybe every 100 meters. Yeah, it depends on, you know, which category it is. I think here, I mean, well, this is just what we said. So I guess for home or office use, right, twisted pair is actually sufficient, right? You know, sort of fast enough, right? Yeah, you know, the bandwidth is high enough. Obviously, yeah, for some other kind of more specialist cases, right, yeah, it's probably right not fast enough. Right, then if we look at the next one, so this is basically just an improvement on twisted pair, yeah, even though it's older. Right, so again, it's going to contain insulation, right, to reduce the interference, and I guess what here they say outer insulation. I think the copper mesh, well, that's also going to be insulation. Yeah, so I guess here's kind of like 3 layers of insulation, really. And then actually, right, if we look at it, well, so I mean, this small copper wire, I mean, this is the thing where the data is actually going down. You know, like even yeah, okay, so even though you know we've got this kind of big like circular wire, right, the actual copper wire where the data is going down, you know, it's quite small. Or yeah, kind of big circular cable. Right then, well, the use case is mainly going to be used for broadband connections. And I suppose this is kind of like special case broadband connections. I mean, most people don't really have it in their house, but you might have it, for example. I think one thing they say is that sometimes you, right, okay, so let's say you have fiber optic as sort of the main, I don't know, like city line, for example. But then if you think, okay, let's say going from the road, right, to your individual house, well, you know, that individual, yeah, I guess, okay, right, that connection to the individual house, right, can sometimes be coaxial. Although I think these days, you know, they're probably trying to just replace everything with fiber. Right, yeah, okay, so I guess this is also quite common. It's also used for, well, the old TV or old radios, yeah, CCTV, and yeah, I guess just various kind of more like industrial cases, right? It's not really used sort of residentially that often. Right, then if we just look here, so actually this one's quite easy, basically just moderate for everything, right, in the middle. So, well, moderate cost, right, yeah, just, right, okay, obviously more expensive than twisted pair, but cheaper than fiber optic, right, which we'll see next. Likewise, the bandwidth again, right, so we're higher bandwidth than twisted pair, right, but lower than fiber optic. Right, again, what interference is the same, right, so yeah, more than, right, okay, sorry, okay, right, yeah, okay, less affected by interference than twisted pair, however, more affected by interference compared to fiber optic. Right, again, the attenuation, so we say, well, yeah, I guess, right, okay, so, right, yeah, okay, let's say lower attenuation than twisted pair. So let's say that this is, all right, well, let's say CA, right, coaxial. Whereas in contrast, you know, for example, well, this is going to be twisted pair. But then if we say fiber optic, yeah, of course, well, fiber optic is going to be the best, right, it's going to have, well, the lowest attenuation. Right, and then, well, actually, like, these two are basically the same, because if you think, well, I mean, the attenuation basically defines how many repeaters we need. So since twisted pair, you know, attenuates the most, well, therefore twisted pair requires, you know, the most repeaters. Right, since coaxial is in the middle, well, of course, yeah, we require kind of, yeah, a medium number of repeaters. And while fiber optic obviously attenuates the, you know, the least, right, therefore what we need the fewest number of repeaters. So I think, I mean, that's why it's quite easy to remember. I mean, coaxial, well, basically it's just the middle for everything, right? Kind of, yeah, I guess, well, better than twisted pair, right? However, of course, you know, more expensive. But yeah, worse than fiber optic, you know, however, well, cheaper than fiber optic. Yeah, and actually, like, one thing I will point out that actually the books claim that coaxial has the highest attenuation. However, all the sources I found online were generally saying that actually twisted pair has higher attenuation. And that was even from, for example, websites that were, you know, manufacturing these cables. So, I mean, like, right, okay, yeah, so I'll say, right, if anyone thinks this is wrong, then I guess, well, let me know in the comments. But, I mean, based on the sort of cable manufacturers' websites that I found, yeah, they were saying that, well, yeah, okay, they were saying that twisted pair has a higher attenuation, right, than coaxial. Alright, so fiber optic, well, yeah, here then, well, light is transmitted at high frequencies through glass tubes. And I guess, well, of course, here we can see what the individual fibers, yeah, like kind of blue on blue, right, quite difficult to see. Right, so the current world record speed, well, I guess not speed, I mean let's say bandwidth, really. Yeah, bandwidth, right, and, well, that's going to be, well, 1 PB per second. Now, PB, hopefully, well, I guess, yeah, maybe we remember, right, that's going to be peta, right, so petabits per second, or 10 to the 15. Now, actually, I mean, well, peta you don't need to know for the exam, although, yeah, that's just, I guess, just extra information. And then what I think, yeah, 10 to the 18, I think that's going to be exa. Yeah, I mean, hopefully that's not wrong. Right, however, the current commercial solutions tend to be about 100 gigabits per second. So yeah, of course, we can actually get as fast as what they get in the lab, right? Not in those controlled environments. Right, and then yeah, hang on, let's just change the color. Right, okay, so these bandwidths are per glass fiber or per tube. Right, and because fiber is less affected than interference, yeah, okay, less affected by interference than copper cable methods, right, either twisted pair or coaxial, then basically, I mean, we can just keep adding more and more fibers. Like, if you think twisted pair, I don't know, I think twisted pair maybe there's like 6, 7, right, maybe 8 twisted pair wires. Like, and yeah, and I guess like we can't really just add, 100 twisted pair wires, right, since there's probably going to be too much interference, right, too much crosstalk. However, since fiber is the least affected by interference, the least affected by crosstalk, then in theory, like we could probably have a fiber optic cable with like thousands of individual fibers. Yeah, just obviously to get the bandwidth of the total cable, yeah, higher and higher. So for example, if we wanted a 1 terabit per second, then of course we can just use 10 100 gigabit per second fibers. However, of course, if we look at this, right, one petabit or petabit per second, presumably this is just for one fiber, right? Yeah, I would assume. Right, okay, so it's stated that fiber optic cables could support a, I guess, theoretical bandwidth of 1,000 times higher than twisted pair, right, or coaxial cables. And yeah, okay, so try to have a think of why that is. And actually, I think I saw that, I mean, some places were saying coaxial was sort of, 2 times faster. Some places were saying, 80 times, I guess, yes, 80 times more bandwidth than twisted pair. I guess really, again, it's just going to depend on the coaxial cable, right? It depends on the twisted pair cable. But yeah, right, okay, so I guess here, right, just think, like, what have we said so far about the 3 factors that affect the bandwidth that are going to mean that, fiber optic has a much higher bandwidth, basically. Alright, so if you had a thought, some people might be thinking, of course it's the speed of light, right? The speed of light is 300,000, or I think 300,000 meters per second, or maybe 300,000 kilometers per second. I can't remember. However, like if we actually think, and yeah, okay, actually, right, this surprised me, but the actual speed of voltage, right, the speed of electricity on a wire is actually 50 to 90% the speed of light. So actually, that's not really that much of an issue, right? I mean, just 2 times slower, at the maximum. Maybe here where it's only sort of 10% slower. So actually, the main reason is going to be the frequency of light in a fiber optic cable. Let's say 10 to the 15 hertz is sort of much greater than the frequency of electrical signals in copper wire, which that's just going to be I guess 10 million hertz. And I think this one we said, right, so why do you think increasing the frequency increases the amount of data we can transmit per second? And I think here I do just have a picture. Right, so here are the graphs then for y equals sine x and y equals sine 10x. So I guess of course sine 10x is going to be this blue one. Obviously sine x, right? That's obviously this red one. So hopefully you can see, okay, so if we say so if we assume that a peak is 1 and a trough is going to be 0, and if we say a peak, right, of course that's the top part, right? A trough, that's going to be the bottom part. Right, hence we can say a high frequency equals more peaks and troughs per second, right? Therefore higher bandwidth. Since again we're saying of course this is a 1, 1, 1. As of course, I mean here there's just going to be a lot more ones and zeros per second effectively. Just a lot more data transfer per second. So if we actually put this into a real life example, let's think then between 4G and 5G internet, right, which has a higher frequency? And I think people probably know 5G has a higher frequency. And because of this, this is why the bandwidth is higher. Because of this simple property. Right, then if we just look at the advantages, probably you can guess, extremely high bandwidth. Right, it's also got the lowest attenuation. I think, do we say it only needs a repeater every 100 kilometers? Of course, low need for repeaters. And again, of course, right, attenuation and repeaters, I mean, they're just related. Since if it attenuates at a low rate, then of course we need few repeaters. If it attenuates at a high rate, then of course we need many repeaters, right, close together. Right, it's also going to be the least affected by interference, right? That's why of course we can have hundreds of fiber optic cables, bundled into a single wire. Right, hundreds of fiber optic tubes, right? The glass tubes, kind of bundled into the single, cable, right? The whole thing. Right, however, the disadvantage, it's going to be expensive. Also, it's going to require specialist equipment. yeah, I guess it's sort of slightly more technical to set up, right? It also requires, more experience. Yeah, I guess it's, more difficult. Yeah, more difficult for engineers to install as well. Right, so let's say, well, ignoring price, like, why doesn't everyone use fiber optic? If it's just so much faster. And I mean, yeah, maybe you can think like this is not really a technical reason, but I mean, it's kind of like what we said. Okay, since well, for home or small office use, Twisted Pair supports up to 40 gigabits per second, which, well, of course, yeah, I mean, just for homes, right? I mean, that's going to be good enough, right? Because if you think, well, I mean, probably what a one, let's say what like a, yeah, I don't know, okay, let's say like a 2 hour HD movie. Well, that's probably, let's say, what, 4 gigabytes. So if we say, well, 4 gigabytes, well, that's going to be times 8. Well, that's going to be 32 gigabits. So if you've got like a 40 gigabit per second connection, then in theory, you could download a 1 hour movie in like 1 second. I mean, well, less than 1 second. In reality, you're actually not going to be able to do that because, well, one, the actual speed of your SSD is going to be slower than that. So yeah, the SSD is not going to be able to write it fast enough. Also, you're going to have a problem. Well, yeah, I guess. Well, I mean, probably I don't know. Okay, probably like the ISP is not going to support that speed, and or yeah, that bandwidth. And also, well, the server. Okay, so the actual server that is sending you the data. I mean, they're also not going to be able to send that quickly. So in effect, it's just pointless. It's kind of like having a space rocket, but only being able to use it on like the highway or the motorway. It's like, yeah, what's the point of having something that can go 20,000 kilometers per hour or yeah faster, on a road that you can only do 100 kilometers per hour. And yeah, I guess there's also another thing. I mean, right, we can say, well, probably only huge companies, yeah, some massive offices, also universities, hospitals, right, places with lots of people, right, things like ISPs, right, I mean, they would need it. Also, well, some companies have kilometers of probably hundreds of kilometers of twisted pair. So switching to fiber optic, well, it's going to be right costly. It's going to be time consuming. Yeah, it's going to be kind of I guess annoying, right? Just yeah. Right, so if we just have a comparison now, actually, yeah, I'm going to put this one in red since again, like the sources online actually disagree with this. But basically, this whole thing, I mean, I don't know. Okay, maybe it looks like a lot of information, but it's actually quite simple. Because if you think, well, twisted pair, okay, it's going to be the worst, right? But it's the cheapest, and again, right, that's for everything. Coaxial, well, it's in the middle, and again, the middle price. Fibre optic, well, of course, right, it's the best for everything, right? However, right, it's the most expensive. So yeah, I mean, hopefully that relationship is right quite easy to remember. Right, so then if we look at some of the wireless technologies, or yeah, the wireless mediums, so well, Wi-Fi is going to work by transmitting data over radio waves, and it's going to use well different channels. So these are kind of groups of frequencies, and this is used to reduce interference. So right, so okay, right. Imagine we have 10 different Wi-Fi networks, right? Each with 10 devices all communicating on the same frequency. So effectively, what 100 different devices. Well, if we had like 100 different devices all communicating on the same frequency, right? Of course, well, then we're just going to get this interference here. So obviously, yeah, this red and blue wave, right? Then if we combine them together, constructive interference. Okay, so right, okay, I guess here, okay, this is called constructive interference, where we've actually got like a bigger trough. Whereas, for example, at this point here, okay, so where we've got a sort of a positive right here and obviously negative here. Well, of course, that's caused sorry, okay. Yeah, that's caused destructive interference. It should just cancelled them out basically, or yeah, cancelled out the amplitudes. Yeah, so well, we're going to get interference, right? And yeah, that's all it's saying. Right, so to solve this then, well, I guess, yeah, different channels, right? Well, yeah, okay, different frequencies can be broken down into separate channels. Right, and yeah, well, okay, right, so to reduce interference then, different networks and devices should communicate on different channels. So rather than having 10 networks on the same channel, right, you can actually go into the router settings. And usually, I mean, well, usually you're going to do this just by typing in the IP address of the router, which for a home router, I mean, probably it's going to be like 192.168, right? Yeah, maybe 0.1. I mean, it could be something slightly different, right? I don't know, yeah, maybe 1.1 or something like that. But what, yeah, I guess like whatever that's going to be, like usually you can find it on the underside of the router. Yeah, otherwise, just go online, right? Type in your router's model, and then type in the sort of, I don't know, I guess like IP address of, and then yeah, that particular model of router. Right, if you go in here, okay, you can actually see it on the settings, right? Yeah, all right, okay, so okay, you can see a setting, right, for the number of channels. So like if we have here, Yeah, all right. So let's say we're doing what 2.4 gigahertz and well, let's say 2.5 gigahertz. So 2.4 gigahertz, well, this is going to be what the lowest channel, right? The sort of lowest frequency. Obviously, we're at 2.5 gigahertz, right? The highest frequency. Now, if we split this network, let's say, into two channels, well, then of course, what we're going to have one channel here. I guess one channel here at what 2.45, and then of course, well, yeah, the other one here. So of course, well, channel one, channel two. So we would say, okay, right, some of the devices are going to communicate, all right, let's say, yeah, here in these frequencies, right? Some of the other devices are going to, communicate here in these frequencies. And of course, well, because we're separating them out, right, we're not going to get the interference, or, well, I guess, yeah, okay, so we're not going to get as much interference. Whereas, of course, like, I don't know, okay, let's say we were using like 14 channels. So I think 14 channels is a common one. Well, then, of course, yeah, we're just going to have obviously one here, one here, one here, right, just separating them out even more. Which I think, well, yeah, hopefully you can sort of see that here in the diagram. Yeah, just kind of understand what that's saying. Right, we can also say that the bandwidth utilization is increased because, well, data can be sent on a quiet, okay, rather than congested channels. So yeah, if one channel has, lots of people, right, maybe it's having to wait. I guess instead we can just, switch that device to be sent, yeah, I guess to send and receive data on a quieter channel. And I think probably what you can do, well, I mean, definitely you can, change the channel for the router. And you might be able to have it where, yeah, I guess even, different devices on the same network can also, probably communicate over different channels. All right, so yeah, then if we get to the next thing, well, is right, guided versus unguided media. So guided, well, basically means we can kind of aim the signal. And I've, yeah, sort of put that in quotes. Right, so well, by definition, cable is going to provide a one-to-one connection, right? Hence, are guided, because of course, well, if we have A and B, well, of course, with a cable, right? We're just getting a direct connection between A and B. Like, yeah, of course, right? The signal is not, going out in all directions like this. So yeah, that's going to be quite good in many cases. However, unguided, well, this means the signal is sent in all directions, and in some cases, right, this is actually useful, right? E.g., a wireless access point. So again, a wireless access point, well, like if we're thinking of a home router, right, a home router is going to provide the wireless access point. And if you think, well, if we have a router, what the wireless access point, right, basically that's just going to be the antenna, right, the thing that's, sending out the signals, basically. Also, well, radio tower, right, TV station, and right, they're going to send the signals, well, spherically, right, so in a circle. And of course, well, that means, yeah, in all directions. Because if you think about that, well, if you've got like a TV tower, then you wouldn't want it to only send signal in one direction. Because, well, I mean, what's going to happen, people on, like, let's say this side of the city, or people on this side of the city, right, they're not going to be able to sort of listen to the radio, yeah, for example. Or, yeah, they're not going to be able to, get the TV network. Alright, so, yeah, let's think about, do you know what type of electromagnetic waves a remote control uses? Right, e.g., well, yeah, TV remote, air conditioning remote. So if you know that, well, it's going to use infrared. Yeah, I mean, I think it's always going to use infrared, right? Maybe some use different, but yeah, probably always infrared. So try to think, okay, what happens if you don't aim the remote control directly at the receiver? So, yeah, of course, well, I mean, let's say if the TV is here, and, let's say instead, you're aiming the remote control here. Now, I mean, of course, there's going to be a little bit of leeway, but if you're, like, completely, like, 45 degrees off, well, here, right, the TV is actually not going to receive the signal. So what we can say then is, well, yeah, well, I guess electromagnetic waves with higher frequencies are more guided than those with lower frequencies. So I guess, yeah, okay, we're kind of saying, right, okay, if it has high frequencies like this, right, it's going to be quite guided. Whereas if it has, low frequencies, well, I mean, yeah, I guess, low frequencies, well, it's just going to go in all directions. And I think, yeah, I kind of logically, right, that seems to make sense as well. Right, so if we just look at the sort of relationship, right, so if we start then with what low frequency radio waves, and going up to a high frequency infrared. So right, okay. So as we increase the frequency, the bandwidth is going to increase, and this makes sense because, well, as we said before, right, if we have a higher frequency, well, we just have more peaks and troughs closer together, right? Therefore, right, we're sending more data. Right, attenuation. So, and this is going to be a bad thing, right? So the higher the frequency, well, the more it will attenuate. So a high frequency, of course, is going to lose the signal strength quickly, right? Whereas a low frequency, well, it's going to lose the signal strength slowly, right? That's why, well, of course, yeah, radio waves, well, I mean, they're used for, well, radio, right, as the name suggests. Because, of course, if you think, well, a radio station, right, of course, that, that has to broadcast for, like, sort of, well, hundreds of kilometers, right, thousands of kilometers, right, if you want to cover, everyone, like, in the, well, city, country. Right, so right, okay, so because of that then, right, if we have a low frequency, well, of course, yeah, we don't need many repeaters. Whereas, well, if we have a high frequency, well, because of this, high attenuation, right, therefore, well, we do need many repeaters. Right, the directional focusing. So we say what the as it's okay. So as the frequency increases, then what basically this means what it's getting more guided. Whereas yeah, if we have a low frequency, well, I mean this is kind of more unguided, effectively. Right, then if we talk about the penetration through a wall, so radio waves, well, of course, right, they can go through walls. Whereas yeah, as we have high frequency, well, then it's going to get blocked by walls. And I think yeah, okay. Then if we see interference, well, it says right, there's no systematic trend. So if we think, well, 5G and 4G again, well, 5G has a higher frequency than 4G, right? That's why it has a higher bandwidth. However, 5G has a shorter range, and maybe people have noticed this, that if, for example, you have a router, okay, so kind of related to this, right? It's also more likely to get blocked by walls, because, like, honestly, okay, when we say shorter range, I mean, well, the reason it has a shorter range is because it's just getting blocked by the air particles, right? It's getting blocked by I guess just I guess the atmosphere. Um, so what we can say, well, right, okay. So if you have a router that's transmitting, both kind of regular like 4G signals, right, and also has a 5G signal, often you'll notice that if you look at the sort of internet bar, well, okay, let's say for the regular signal you're getting sort of 4 bars, right? But if you look for the 5G signal, right, you're only getting 2 bars, and of course, right, that's again because you're too far away, right? It's getting blocked by the walls. I mean this one about high frequencies causing health issues. I don't know. I mean maybe that's true. Obviously, like if you take it to the extreme, gamma rays, well, yeah, of course, I mean that's going to cause cancer. Um, but yeah, I don't know. I mean that's kind of maybe some like conspiracy theory, right? People like burning the 5G towers. I guess not really related probably. Alright, so yeah, if we just look at the Wi-Fi advantages, disadvantages, I guess having talked about those extra things as well. Right, so it's going to be accessible with portable devices, right? So laptops, tablets, phones. Right, also no cables are required, and alright, okay, the setup is easy, fast. Yeah, of course, just sort of plug it in, type in the password, right, just connect. Right then, suitable for public locations, right, cafes, hotels, transport. Of course, where people are on the go. And in many exams, they have questions like, why would a university campus want both, let's say, wired and wireless? And of course, wireless, right, you can mention these points, right, no cables, things like that. Since you're not going to want it where, if, of course, okay, let's say if someone is, walking between classrooms, right, they're, walking it in and out of the library, I don't know, maybe just like having a picnic right on the grass. Well, of course, they're going to want to be able to, use something without cables, or use something right on the move, basically convenient. Right, have a disadvantage where it's going to have lower bandwidth, I guess, and this is compared with the wired approaches, or the wired transmission mediums. Right, it's also less secure than the I guess wired transmission mediums, and this is because anyone can listen in. However, the data should ideally be encrypted because if you remember, of course, Wi-Fi. I mean, I guess kind of as the logo suggests, like here, I mean, of course the waves are just going in all directions. Right, therefore anyone can listen in, to the data that you're sending. Although again, right, since it should be encrypted, if you're using a Wi-Fi password, then in theory, people, of course, people shouldn't be able to actually understand that data, right, unless they somehow manage to crack the password. Right, also another disadvantage were high absorption rate, right, e.g. blocked by walls. So I guess absorption rate you can call attenuation. So high attenuation. And I guess relatively short range, again, right, 20 to 150 meters, right, so high attenuation. Alright, so I think, just finally then, let's talk about satellites. And satellite, there's going to be different types. One is geostationary, so they're going to stay above a fixed position on the Earth. And here we only need 3 for whole Earth coverage. So what that's saying is, okay, this is the Earth here. So let's say, this is, satellite 1. Okay, right, this is satellite 2, right, this is satellite 3. So what we can do, of course, alright, 1 can send signals to 3, right, 3 can send signals to 2, of course, 2 can send signals to 1. So effectively, you're getting this triangle. Now I've just realised it looks kind of like the Illuminati triangle, to be honest. Alright, so then there's also MEO, right, medium Earth orbit. Right, this is going to be useful for GPS. GPS, or I guess big S, right, etc. Right here, then we require 10 for whole Earth coverage. And low Earth orbit, or LEO, right, it's going to provide mobile phone network. right? 50 are required for full Earth coverage. And if people know, well, Elon Musk, right, Starlink, they operate only 340 kilometers above the Earth's surface. And because of that, well, that's why, one, you're going to get what the right. So, well, one, you're going to get low latency, right? I guess the low time, from your signal here, well, to reach the satellite, and then also get sent back to the receiver, right? It's going to take a low time, right? Low latency. The other advantage, well, the signal strength is also going to be stronger, because of course, well, if you're sending signal, a longer distance, well, you're going to get what a sort of slightly kind of higher rate of attenuation, right? As the signal, inevitably kind of fans out a little bit. Right, and then here it just says, well, the Van Allen belt is going to contain high levels of electrically charged particles, hence satellites aren't placed there. And yeah, well, here we can see what they say the upper Van Allen belt, I guess what above 15,000 kilometers, and what the lower Van Allen belt, I guess what between the low Earth orbit and medium Earth orbit satellites. Then if we look at some of the use cases, it says, well, satellites can act as a component in a network or directly communicate with ground-based components. So when it says directly communicate, well, of course we can have, let's say, person A here, person B here. I guess what we can, send some signal to this satellite. This can, send a signal to person A. So in this case, of course, well, this is directly communicating. Now, instead, we could have it, and this was kind of like the diagram I drew on the previous slide, where, well, of course, what if we have, satellite 1, right, satellite 2, satellite 3. In fact, let's do that further apart. Then, of course, what we could have, say, person A here, right, person B, maybe like in Australia or something. And, of course, what person 1, probably, they're going to send to their ground-based, ground-based antenna. Right, this ground-based antenna is then going to send, to satellite 1. Right, of course, this satellite 1 can then send to satellite 2. Right, there's going to be another ground-based antenna, right, of course, that's going to send, right here, right? So satellite 2 is going to send to this ground-based antenna here, and then of course, well, this ground-based antenna is then going to send to B. Hopefully that makes sense. Again, right, of course, well, either we can directly communicate like this, right, or we can combine it as part of a greater network, in order to communicate, or let's say here just via relay satellites. Right then, well, ground-based components can be further apart than the network without satellites, since relay satellites have a large view of the Earth's surface. Now, if you think, so a relay satellite, this is going to have a high altitude, and probably you can think, that of course, well, if we have something close to the Earth, let's say here. Now, because this is close to the Earth, we can only kind of see a small part of the Earth. Whereas if, for example, we have a relay satellite far from the Earth, well, then of course, what that can see, a much greater, I guess it just kind of has a much greater segment, or the I guess kind of the view of the Earth. I think hopefully that makes sense. However, since there's large distance involved, then we're actually going to we're going to get high latency as mentioned, and the latency, well, the definition basically what is the time to receive the first byte, how long it takes to actually start receiving the signal, because of course, that's just because the long distance is involved. So I think, right, hopefully that makes sense. And again, of course, well, this is talking about in comparison to just, cables on the Earth, right? So in comparison, satellites going, a longer distance than cables. Right, however, well, in reality, well, because of the high cost, I guess the high latency and low bandwidth, then satellites are really only used for specialized applications, where, well, alternatives, e.g. fibre optics, aren't available. So, for example, I guess your internet access for mobile phones, since, well, of course, mobile phones, we can't have wires connecting to our mobile phones. We're also, well, GPS, things like, well, military, tracking. We're also, well, internet access in remote locations, also after natural disasters. So I think Antarctica can only be accessed with satellites. They don't have any cables. Likewise, of course, some mountainous region. Also, well, internet access on planes, which I think is becoming more and more common. I think this one basically just the same thing again. So the advantage is, well, it's accessible from virtually anywhere, right? Even if the local infrastructure is being destroyed, e.g. in a natural disaster, maybe a war zone. So I think people are probably probably aware that what they're saying that, well, Starlink, right? This is being used, in the Ukraine war. Probably other places as well. Where of course, I guess Russia has destroyed the sort of typical ground-based internet. Yeah, right, and again, well, yeah, I guess so. Well, remote locations right after various disasters. Right, also, well, specific use case, right, GPS, right, mobile phone network. Yeah, obviously, well, taking photos of the Earth, right, like sort of Google Maps. Right, well, disadvantages, well, of course, it's expensive, right, low bandwidth, and I mean, actually, like if we think, well, the bandwidth of the entire satellite isn't really that low. It's pretty good. But the problem is, well, of course, you have to think, okay, right, that satellite is shared between like thousands of people. Like, obviously, it's not going to be economically viable for each person with a mobile phone to have their like own individual satellite assigned to them. So yeah, of course, because you're sharing because you're sharing the satellites between thousands or millions of other people, right? I mean, that's why the actual, well, of course, yeah, what the speed of the mobile phone network is, of course, right, slower than, for example, your home router. Right, well, again, we're high latency, well, because of the distances. And yeah, of course, we're extremely complex. I guess, yeah, launching rockets, building satellites. Yeah, I guess, yeah, not too easy. Right, another problem, well, repairs are going to be difficult or even outright impossible because, well, once it's in space, yeah, there's probably, limited amount you can do, especially if it's a hardware problem. Software problem, not so much, right? Generally, they should be able to update it. But yeah, obviously, many hardware problems, yeah, it's just right, impossible. Right, then if we look at some of the legal issues surrounding transmission media, I mean, this is in the book. Like, yeah, maybe they might ask this in the exam, although probably not. Like, maybe in the ethics chapter. Right, so do you think then you can set up an antenna and just, start randomly transmitting data? So maybe people have heard of some cases about this. So actually, right, okay, and like probably this depends on the country. So yeah, it's obviously a little bit different. Right, on unused frequencies, I mean, generally you can, but if the frequency is used by, well, let's say the military, the government, yeah, I guess what, like an existing TV radio station, then, well, I guess, well, I mean, probably you're going to get into legal trouble, or maybe fines, yeah, even prison, right, if the offence is severe enough. Let's say, well, if you're, for example, trying to, jam the military signals, yeah, if you're transmitting signals, on the same frequency as the military, of course, right, that's going to interfere with all their communication, which, yeah, they're, probably not going to be too happy with. All right, so yeah, everything that so right, okay, are there also going to be legal issues for cable? And this one, I suppose, well, it's going to depend on the country. So if it's a private company installing cables, then probably they have to get permission to dig and lay the cables underground from the landowners, right? Yeah, e.g., the farmers, right, whose land they're building the cables under. Right, if the telecoms companies were owned or partly owned by the government, then I guess the company is probably going to have less issues because, well, of course, I mean the government can make the rules, right? They can decide where to build it. Yeah. All right, so I think all right, okay, so yeah, all right, yeah, not a recap. Right, okay, well, we've looked at the following transmission mediums. Right, well, twisted pair, yeah, coaxial, right, fibre optic, right, of course, all wired. And then, well, for wireless, right, Wi-Fi and satellites. Now, I mean, I think in the exam you can also mention Bluetooth as well. Yeah, although maybe they don't mention it too much in the books. Right, so which do you think would be good for local versus global communication and why? So yeah, try to have a think again. Think about the bandwidth, think about the attenuation, the interference, yeah, the need for repeaters, the price. So if we think then, well, for home small office use, or as we said, well, twisted pair and Wi-Fi are going to be a good option. Well, of course, I mean one since the bandwidth is high enough or it's good enough. Of course, well, Wi-Fi, as mentioned, what it's going to provide the advantage. One, you can connect devices that can't support wires, right? For example, phones, tablets. Yeah, they're not going to support a wired connection. Two, of course, it's convenient because, well, I mean, you can use you can use the Wi-Fi right in different locations, right? Whether you're in the living room, right, the kitchen, maybe outside in the garden. Right, I mean, coaxial is also fine. However, it's going to require hardware that's less common these days. Yeah, and I think most people have probably not really seen a coaxial connection. I think, I mean, well, certainly you're not going to have a coaxial connection, from your switch to your desktop. Yeah, it's going to be more for sort of specialized applications, really. Right. Yeah. Okay. So I think we said that. Right. So yeah, the bandwidth is sufficient. Right. Yeah. Wi-Fi again. Well, convenience. Right. People can use non-computers. Right. Portable devices. Right. Move around. Right. If instead we look at global communication, well, if possible, then we want to use fiber optics. And the reason why extremely high bandwidth, and also so cheaper price. Right. But this is compared to satellites. Of course, right. Fiber optics, right, it's more expensive than twisted pair and coaxial. But yeah, I mean, compared to satellites, right. Of course, it's much cheaper. However, if, for example, there is some situation where like requiring GPS or a mobile phone network, right, connections in remote locations, yeah, I guess after natural disasters, right, then satellites are of course needed in those cases, right, when nothing else is suitable. All right, so yeah, right, okay. So I think yeah, this is the recap then. So how do the transmission mediums rank in terms of well cost? Yeah, how about the attenuation need for repeaters, right, amount affected by interference? Yeah, and also the bandwidth as well. So okay, right, try and pause the video. I tried to think about all of these. All right, so if you pause the video and have a go, well, let's have a look at the answers. Right, okay. So if we say Wi-Fi, well, Wi-Fi is going to be cheap, right? However, the bandwidth is quite low. Then while the interference, attenuation, repeaters, right, these are all bad. So I guess yeah, lots of interference, lots of attenuation, right? Therefore, yeah, well, right, of course we need high, yeah, lots of repeaters, right? Since we have high attenuation. Right, if we say satellite, well, yeah, the cost, right, very expensive. I mean the bandwidth. Yeah, I mean again, okay, so right, the bandwidth of an individual satellite is okay, but again, since you're sharing that between thousands or millions of people, right, well then it's going to be very low. Of course, if you're talking about your phone connection is going to be slower than, for example, your home Wi-Fi. Right, interference. Yeah, I mean this is quite high. Again, I mean this of course depends on what waves are being sent, right? If it's well, oh yeah, right. Okay, sorry. Yeah, the attenuation depends on what waves are being sent. Now, right, like if we say here, and I think it probably says here actually, like if we're talking in the vacuums of space, then actually the interference is not that bad. However, if you're talking about on Earth, right, where of course yeah, there's other electrical signals. Also, if you have things like well, I guess yeah, clouds, right, charged atmospheric particles, all right, solar flares. Well, yeah, of course, right. I mean, then it is going to be affected by the interference. Right. However, we can say well, the need for repeaters is going to be low. And I suppose I mean okay, right. This seems like it's in contrast. Now, the reason I say low is because well, since most of the distance it's traveling is in space. So in space, well, of course, we actually don't really need many repeaters, right, since it's a vacuum. But I mean, once it gets on the Earth, okay, yeah, once it gets, in the Earth or in the atmosphere, right, well, of course, right, then attenuation is going to increase a lot. All right, so well, the next one, so twisted pair, we said what is cheap, and then well, basically everything else is going to be bad. Although of course, it's good enough for just home use. Coaxial, well, I mean, yeah, just in the middle for everything. Right, fibre optic, well, expensive, but yeah, of course, well, extremely good performance, right, for everything else. Right, then let's think then, so what are the advantages, disadvantages of wireless compared to wired transmission? And again, pause the video, have a think. Right, so we say, well, wireless, well, of course, right, we can use it for portable devices, remote locations, right, it's convenient, easy to set up. Yeah, of course, we can move around. However, well, disadvantages, it's going to have lower bandwidth and also less secure. And of course, well, less secure, since everyone can listen in, right, since we said what the, yeah, right. Okay, so what? Okay, right. Let's say the waves are going to be unguided, right? I mean, that's probably the sort of best term to say it. And of course, yeah, unguided means of course, yeah, the signals are sent in every direction. Yeah, and of course, well, that's why it's less secure. However, it should be encrypted, right? Which should kind of mitigate against that, right, to an extent. Right. So, well, as for wide, then, right, the advantage was going to have higher bandwidth and more secure because, well, you're going to have one-to-one connection, right? Like no one can access that unless they have physical access to the wire. However, the disadvantage was going to require additional hardware, like cables. Yeah, and I suppose, I mean, for this, you could probably also mention things like attenuation. If you're talking about fibre optic, well, of course, I mean, this is going to have low attenuation over long distances. If you're talking about twisted pair, well, twisted pair actually has high attenuation, right? I mean, similar to Wi-Fi. So of course, yeah, of course, saying or mentioning attenuation things, right? It depends on the actual, yeah, sort of specific medium. That's why I think, okay, like when it says, okay, list, say 2 advantages of wireless or 2 advantages of wires. Yeah, of course, just talk about these general advantages, right? Don't talk about specific things, for specific, right, transmission mediums. Right, then let's think again. So what medium would be suitable for long distance, like cross-country undersea cables? And yeah, what might be preferred for, well, let's say mid-range, right? Yeah, mid-range or sort of large office. And I guess also sort of home, yeah, I guess just, home environments as well. Right, so if you had to think then, well, long distance, we're going to want to use fibre optics. Well, of course, yeah, high bandwidth, low attenuation, right? Hence low need for repeaters. Right, small office, I guess we can use twisted pair, it's cheap, right, bandwidth is good enough for a few devices. And if we have a large office, right, maybe we want to use coaxial, since well, it's relatively cheap, right, of course, well, more expensive than twisted pair, right, cheaper than fibre optic. And again, what the bandwidth is, of course, higher than twisted pair. Alright guys, so yeah, again, super long video, but hopefully that's useful, and as always, well, if you have any questions, just ask in the comments, and yeah, hopefully see you again in the next video.